Hello, everyone. I'm Tianlong. I come from Tsinghua University of China, and I'm honored to share our work with you. I want to introduce our paper, Dynamic Muscular Convolution for Dialect Identification. Let's see the background. Dialect identification is the front end of speech processing systems. Besides, more and more people participate in the dialect activities, where traditional methods have many difficulties to extract distinguishing features for dialects, and these methods are hard to be modeled. Besides, large number of parameters are also a problem that needs to be solved urgently. Common dialect identification models can be linked to speaker recognition, such as Cavg, TDNN, FTDN, ResNet, TDNN, and so on. Each method for dialect identification have several shortcomings. For example, suitable variant is being neglected in different feature scales. Local and global information are often considered separately, and good performance, but ignoring the huge amount of parameters is very common. To address these shortcomings, we propose a new architecture named Dynamic Muscular Convolution, which consists of dynamic kernel convolution, local muscular learning, and global muscular polling. This method further improves the performance and reduces the number of parameters by leveraging these notions. The complete architecture is present in this figure. It is noted that batch normalization and ReLU activation are employed but omitted in this figure. The TDNN network is adopted as a basic skeleton. We modify the first DTDN layer to a dynamic muscular convolution block that represents local muscular features at a granular level and increases the range of representative fields for convolution operation. Besides, global muscular polling aggregates different bottleneck layers features in order to collect information from multiple aspects. The first contribution for our paper is to propose dynamic kernel size convolution. Traditional convolution is generally a single kernel size, but we innovatively propose a dynamic kernel size convolution method. The dynamic kernel convolution is a dynamic channel selection mechanism based on softmax attention. Specifically, the structure of selection mechanism in dynamic kernel convolution is illustrated as follows: statistic polling linear softmax classifier, where statistics polling is aimed to collect channel information from a special dimension. The subsequent layers are aimed to assess the importance of different branches. We can obtain the softmax weight of two branches of two linear layers and softmax activation function. Finally, the dynamic representation indicates the element-wise dot production sum of different convolution operations. The second point is to use the idea of local muscular learning. Traditional neural network usually use a single input and output within the layer. Inspired by the residual connection with ResNet layer in REST2Net, the local muscular learning is adopted to improve representation performance within convolution. Local muscular learning refers to the multiple available receptive fields at a more granular level. As shown in the figure, we evenly split a feature into S feature subsets, denoted by Xi. A group of features firstly extract features from the corresponding feature subsets. Output features of the previous group are then sent to the next group of features along with another group of input features. Each part of the operation here is the dynamic kernel convolution I proposed above. Local muscular learning can achieve more discriminative dialect representations at a more fine-grained, foreground level. The third point is considering that we have the idea of local muscular learning. Can we let our entire model, like transformer model, have a global information control? So we put forward the concept of global muscular polling. Previous work concluded that feature aggregation at different layers can improve the accuracy of speaker embedding models in speaker verification tasks. The bottleneck feature is a kind of high-level information integration. Therefore, we aggregate different bottleneck features in channel dimension and send them to statistic layers for the purpose of enhancing the dialect classification capabilities. Then global muscular polling layer calculates the mean vector mu as well as the second-order statistics in the form of the standard deviation vector sigma over a frame-level feature. The above is the improvement over the entire frame level. In the OLR Challenge 2020, additional training materials are forbidden to participants, and the permitted resources are several specified this size. We leverage AP17 OL3, AP17 OL test, AP18 OL test, AP19 OL DV, AP19 OL test, and AP20 OL dialect as our training set for dialect task. All of the training materials are collected permitted resources, which including 16 languages. The dialect identification is evaluated and ranked in OLR Challenge 2020. From the table horizontal result comparison, we can observe that the dynamic muscular convolution method performs better than other teams' model while operating in the same dialect. Comparing with OLR Challenge 2020 leaderboard number 1, our model can achieve 9.2% C average and 45% equal-average relative improvement with only 2.9 million parameters respectively. The table shows the performance of ablation study on AP20 OLR dialect task. The softmax output scores of 3 target languages are analyzed in the evolution. All-purpose model outperforms the SOTA system submitted to OLR Challenge 2020 in equal-average. The proposed dynamic multi-score convolution method achieves the best performance in all metrics including C average, which suggests that the proposed method is effective for dialect identification. Results demonstrate that the model with AAM softmax is potential to achieve better accuracy than those with softmax loss function. Comparing DTDN-based method, we discover that operation of dynamic kernel convolution is helpful for dialect identification. Local muscular dynamic kernel convolution combines multi-score learning with dynamic kernel convolution, further improving the performance and reducing 36% parameters with only 2.5 million by introducing muscular learning. Besides, local muscular learning within the convolution is effective in the number of parameters by the hyperparameters as global and local muscular dynamic kernel convolution denotes a variant of proposed model which adopts global muscular polling. Comparing the results of these models, it can be seen that global muscular polling is excellent to improve the accuracy of dialect identification. Finally, summarized our work. First, we introduced dynamic kernel convolution into dialect recognition for the first time. Second, we propose local muscular learning, which represents multi-score features at a granular level. Thirdly, global muscular polling is used for dialect identification, which aggregates features from multiple aspects. This work is done by Tianlong as Wang as an intern at Kwai company in China. We thank Professor Shouyi and Xiaorui Wang for supporting this work. We thank Wang, Dawei, Zhang, and Xinwang for helping in paper's experiment. Thanks for everyone.
Okay, thank you very much. Now, first of all, thank you for using the OLR data, and we are very happy to see that you get improvement with the data and test the performance using new technologies. Thank you very much. and also welcome to join our next challenge 2021, and it's more challenging if you are happy with.
Yeah.
So any questions from our audience?
This is the strong network. Have you tried this network to other two tasks, including cross-domain and knowledge task?
I tried this model in task 3, and we have changed the SOTA performance, outperforming the leaderboard number 1. And then task 1, I haven't do experiments, and I can try it on task 1. I will try it.
Okay. We expect a good result for other tasks.
Good. Any questions? Other questions, please? Okay, if no, I have several questions, and because this paper is quite interesting, especially the size of the model has been reduced quite significantly, right? And the performance is improved even with the reduced size. The first question is that I think in new approach there are two elements. One is the multi-scale network, right, and the other is the dynamic convolution. I'm not sure if these two elements can be separated, can be tested separately. For example, you have just one particular setting of your dilation, but you still use the channel selection dynamically using something like gate or some other mechanisms to select channel dynamically, but still have a single scale convolution. So is that work, or I mean the contribution of the two elements?
I tried the 3 contribution, and everyone have performance
Improvement.
对对 yes, and we try 3 all in, and improving is best.
Which one is the most significant? Which one is more effective?
Yeah, it have 18% performance improvement.
Yeah. I mean, the dynamic convolution looks quite interesting, right? And I'm not sure how the large size reduction is obtained. It's because they have multi-scale, right? It means that you have more architecture design, and you need more parameters to cover different scales for your model. And on the other hand, you still can compress your model to a small size. So is that because you use something like you cite the dilation or the dynamic selection? But I don't think the dynamic selection can reduce the size, right? This is because you use some smart choice of the dilation structure, right?
We use the dilation convolution to reduce the parameter size, and we use local muscular learning because we evenly split the channel into S features, so the convolution operation can be convolution parameters can reduce largely.
Okay. Right. So yeah, thanks. So another question is I saw the dynamic convolution is to select the channel, right? So this is more like, if I remember correctly, it's more like something like the squeeze and spike network, right? You try to choose some channels by looking the whole statistics and using the whole statistics to select the channel dynamically. But here you use the dilation network, dilation convolution. I'm not sure if you are familiar or you have tested the squeeze and spike network. Not yet. Oh, no problem. I just curious because to me the two technologies looks quite similar. This is just because your results is quite amazing, right? It's out of my expectation. This is I just want to know the architecture. Okay. Anyway, any other questions for this talk?
I have no problems.
Right. Okay. Do you have a team? I'm just curious if you can attend the next OR challenge. Do you have a team, or you have some other colleagues to work with you on the project, or just yourself, or you are supported by your supervisor? Do you like
maybe
to join
in Kuaishou, we will participate in the OR 2021. Yeah.
Okay, you know the 2021, right?
Yeah.
Okay, that's that's remarkable. Okay, thank you very much. And I think if possible, there is any possibility you can try to persuade the Kuaishou to take part in our challenge. It's quite challenging. It's quite interesting, and it's not only the language recognition, but also multi speech recognition. It's quite interesting.
Yeah.
Okay, thank you very much again. If no other questions, I think we can move forward, and I will hand off the microphone. And thank you very much for the presentation again. Thank you.
Yeah.